This is a talk about MetSim, a simulation support tool, which is using meteorological information for short-term planning of hospital services, and is joint collaboration with some researchers at Cardiff, Southampton University, and the Met Office. The project aims are as follows. Well, previous research has been conducted on links between weather and health, in fact dating back to Hippocrates in the 5th century, who identified that epidemics were related to seasonal changes in weather. But it's not really been until the last 30, 40 years there's been much more focus and more detailed research for various conditions. But this has never really been at the kind of whole hospital level for capacity planning purposes, so this is the novelty here. So there are indeed benefits of accurate short-term forecasts of hospital admissions and bed occupancy for managers, in particular over the next 7 days or so. If we can better forecast and more accurately forecast demand and occupancy, then we can better plan for services. Our focus is on non-elective patients, that's i.e. kind of emergency patients who are admitted into hospital. This is collaboration with the Met Office. We've been lucky enough to work with them and two partner hospitals, University Hospital of Southampton and University Hospital of Wales here in Cardiff. And it's been funded by an EPSRC grant for 2 years. Here's an immediate look at some relationships between the temperatures and demand. For Southampton Hospital for a 5-year period, this shows the average weekly mean temperature over that period of time. And this is the related demand figures, or the flows in and the discharges out, and the red line is the net bed occupancy. For respiratory patients, for the very young, aged 9 and under, and for the more elderly, aged 80 and over. And you can see immediately that in the cold temperatures, in the cold winters, we have much higher demand of respiratory admissions, both for paediatrics, perhaps more marked for paediatrics, but also for elderly. The red lines, notice, although there's similar kind of flows in and out, the red line's much higher for respiratory for the elderly, which indicates a higher number of beds occupied, which is due to them staying longer, typically, than the paediatrics. Here's a schematic of the whole process. I'll come back to this later. At the moment, I'll just focus on the components in the middle here, which are where the researchers have worked on. The blue parts are where the Met Office control, and the red parts are where the hospital controls. But we're going to now look at how we forecast admissions and how that feeds into a kind of real-time forecast. And we're going to how we handle length of stay and how that feeds into an occupancy model. So we had a huge amount of data at the outset. I mean, for each hospital, we had 5 years worth of data on every admission, and that contained information on demographic information, their diagnostics and treatment, and their times and routes of admission and discharge. For the same period of time, we had the 5-year period for temperature, humidity, rainfall, vapor pressure, wind, and many others, and air quality data for every postcode for every day. It's a huge data set to handle. And we also had to incorporate things like temporal data, such as what was the day of the week, what was the month of the year for the admission. Was it a school holiday, and was it a bank holiday? Was there any was that useful information in trying to forecast admissions? And I'm not going to go through the whole huge detail here, given the time, but there was a lot of exploratory analysis and data handling that went on early in the project to try and understand and tease out relationships between admissions and these variables. But there are some obvious ones straight away, like just simply day of the week factor is important. This shows for elderly age 75 plus. You can see there's certainly a weekend is typically lower number of admissions compared to the weekday. And so this indicates immediately that day of the week is an important factor when planning and forecasting admissions. We reduced our data, partitioned it in different ways, with a lot of based on a lot of exploratory analysis, but also based on hospitals' preferences. Now they tend to work by age band in 3 categories: paediatrics, adults, and elderly. Given there, and so we split all our forecasts at least by those 3 age bands. Although the actual ages themselves, the boundaries can be changed by the user. We also partition our forecasts and patients by gender. And that's important, we'll see later. And we partition patients by specialty. And again, we worked initially at these 3 super levels of medicine, surgery, and trauma, but we make the comment that the partition is at the hospital's discretion. So although we build initial models for those 3, Hospitals can divide their data set into any way they like based on their treatment codes, and they can produce forecasts for both admissions and occupancy for every specialty combination they wish. But the problem is, if you go down to too fine a level of detail, the numbers are really rather small and the confidence becomes very uncertain. So modelling admissions, well, after a lot of different models and testing, this is the best model we found. So if we let y, I, j, n represent, denote the number of admissions, we had to square root the data, and we have patients of gender I, age group j, one of the 3 age groups, on a particular day n into the future. Then our model is given by that equation there, which was a distribution there, which just follows a normal distribution, where the mean of that is given by that equation. And what's comes out straight away that the important variables in trying to predict admissions are the gender, the age of the patients, the day of the week, as we saw already. In fact, that was true of all specialties. Whether or not it's a school holiday, that has an influence, particularly for paediatric admissions. There's more demand or higher admissions in the school holidays, typically. Now, interestingly, if we look at the mean temperature, if I had to forecast the number of admissions tomorrow, for example, then I need to know what the average temperature is going to be tomorrow. That came up as an important predictor. But very interestingly, I'd also need to know what the minimum temperature was exactly 1 week ago from the day tomorrow. So there's an indication of some sort of lag effect. So we not only need the temperature today, but also the temperature a week ago, the minimum temperature a week ago. We can't precisely explain that, but that's come up time and time again in our models. So it seems to indicate that the temperature last week has an influence on what happens a week later. And there's also some interaction terms here for age and gender and the temperature again. Now, you notice straight away that the only weather variable that's come in there is temperature. We've tried the whole range of variables given to us, but actually temperature itself was good enough to explain the majority of variation in the data. And in fact, it's not a surprise perhaps to meteorologists, because temperature itself is a good proxy for other variables such as humidity and pressure. That model alone explains over 80% of the variation of our demand in both hospitals. So it's a fairly good predictor. Of course, there is uncertainty itself in the weather forecasts, and we are predicting into the future. So the actual mean temperature on a given day n itself is a forecast. Obviously, the Met Office endeavours to give accurate forecasts, but they also provide confidence intervals around their forecasts. So to handle this, we build a Bayesian model where we put uncertainty on the mean temperatures, and we predict admissions then using Markov chain Monte Carlo methods. We actually iterate 1,000 simulations to get our forecasts. Okay, so that's our forecast model for admissions. Now we turn our attention to length of stay. This is the length of stay for Southampton Hospital for the same 5-year period. And what you can see quite markedly is that there's a large number of patients who stay a very short time, just a matter of a few hours. And then if you cut off at 12 hours, then you see there's less patients actually then stay in hospital, and then you get some sort of cyclic behaviour which represents times of day of discharge. But overall, about 30% or so of people stay less than 12 hours. This is across the whole hospital now for non-elective patients, whereas about 20% of patients stay for more than 1 week. So there's huge variability in length of stay, as we observe. And we now need to build a model to try and capture the shape of distributions for the different specialties, for the different genders and different age bands. So how do we do that? Well, there's a number of ways one could do that, but the best way, what we found for this particular project, was to regard length of stay as in terms of a survival analysis or hazard rate. So we consider length of stay n as a non-negative integer number of days, and we consider the hazard rate given by that definition there. And we found that taking a log odds transformation, a quantity we call gamma, was helpful. So for each day n, now going forward, for our forecast, we build a model of gamma of that forecast using explanatory variables in a similar way to the admissions forecast. we found that if working out length of stay, that predicting length of stay, that the age was important, specialty is important, current day of the week is important, and I'll come on to that in a minute, and whether it's a bank holiday. So your chances of being discharged on a particular day is itself dependent not only on your age and specialty, but also the actual day of the week it currently is, and whether it's a bank holiday. Weather, it turns out, is not significant, so we can't we don't see changes in length of stay due to weather. But gender is marginally significant, so a marginal, and so we include it in the model. Here's an example of what it means. Imagine a male patient who has already been present 2 days in hospital with a medical specialty. We work out for that particular patient the chances of them being discharged. Now, if it's currently Monday, Tuesday, or Wednesday, there's a 13% chance that that patient would be discharged. If it's a Saturday or Sunday, though, there's more like a 27% chance. So you can see straight away that if it's a weekend, you have a much higher chance of being discharged, even having stayed the same amount of days. So there's some behavioural element going on here in terms of discharging people quicker or sooner, or more likely at the weekend. Similarly for the elderly patients, but you see the chances on the whole are much less, and that reflects the fact that they tend to stay longer. Here's an example of some hazard rate plots, and expect to see all the details, but you typically get the same kind of profile. There's a chance of being admitted on your very first day, but there's a higher chance of being admitted having stayed 1 day. Thereafter, your chances of being discharged decline the longer you stay, apart from some peak around 7 days. So there's something going on here that after exactly a week, you've been in a week, there's probably a good chance they're going to discharge you after that week. But thereafter, actually, your chances of getting out become less and less. And that's the shape for medicine. And we have to distinguish between the Monday, Tuesday, and Wednesday, Thursday and Friday separately, and weekend. You said the weekend, as I said before, there's a much higher chance typically of being discharged on a given day. So how do we put that all together then in the model where we simulate patient flow? So let's give an example. Let's fix a class of patients, elderly female medical patients. For each day in the interval of uncertainty, we calculate in the following way: the number of admissions and discharges. So at the end of the day, we keep a record of the number of remaining patients segregated by length of stay. So let's imagine that we're at the end of day 0. We have 12 patients who arrived. We have 6 patients who have stayed 1 day, 5 patients who have currently in hospital who have stayed 2 days, and 3 patients who have stayed 3 days. We update 1 day, inserting new admissions, so we just carry forward those numbers across 1 more day, and we simulate 15 new patients to arrive on that day 0. Now, how many of those patients are going to leave? So using our hazards, our log odds model, on a binomial fit, so just a yes or no, is the patient going to be discharged or not in a sampling method. In this example, we've sampled 2 patients to leave immediately after within the first day, based on the log ratio. 4 patients who have stayed 1 day now depart, so that leaves 8 patients. 6 of those patients who have stayed 2 days, 2 of those now leave, that leaves 4 patients, and so on. So we just basically simulate the number of people arriving. We work out, using the hazards, the number of people likely to leave on a particular given day, and we keep track of the number of, therefore, the net number of people in hospital. And we do this in the model thousands of times. In fact, we simulate this 50,000 times in an iterative fashion in our simulation. Here's some example outputs. This is the total number of admissions for pediatrics. And this is an example of what the hospital would get. So they can see the number of admissions predicted for the next 7 days with the associated confidence intervals, which are 95% and the 80% confidence intervals. So you can see here that there's a marked drop in the number of forecast admissions over the weekend, rising again into the next week. The hospital is also particularly keen in looking at net changes in occupancy. Here's an example for medicine female patients. We can see that there's unlikely to be any change in the number of beds over the next couple of days, but then dropping down, we're going to lose patients over the weekend to be discharged, and then rising again into next week. Here's another example, though, for the male patients over that same period of time. Actually, we forecast an increase in admissions tomorrow, and the weekend going down again, but then quite a big rise in admissions over the same period of time. So we can expect maybe 10 more beds required by this time next week than we currently are benchmarked to baseline 0 now. So we might expect a higher demand over the next, in 1 week's time, to prepare for 10 more beds required for medical malpatients. The validation is obviously very important for this, and so we've done this with various pilots, but also we've looked at this retrospectively. We actually built the model for 1 year's worth of data in 2010. Then we tested it on a forecast in 2011, and actually compared our forecast to what actually we observed in terms of number of admissions. Our blue line there represents our model, and it shows a very good fit in terms of the root mean squared error is typically quite low. And in fact, we're typically only about 4 or 5% error on our forecasts over the whole year. The dotted line is what we call persistence. This is for Cardiff now. And this is basically saying if we forecast a number of admissions today, just based on the number that arrived last week, that's it. We take that as a proxy. And you see, actually, that's not good enough. They're just saying the number of people arriving today will be the same as the number of people who arrived this time last week is not sufficient. And you need to incorporate the weather variables and the other factors. And the red line is another good model which we used, which is just simply a 6-week moving average of admissions with some sort of enhancement, which I won't go into details. But that actually does fairly well too, although our proposed model overall is much stronger over the whole year. And that's the equivalent for Southampton. And again, you see for Southampton data, we're getting quite low root mean squared errors in our forecasts. In fact, I should say that the statistical model alone accounts for 80% of the variation in emissions, and the length of stay model accounts for 90% of the variation in length of stay. If I just come back then finally to the schematic. So how does it work in practice? A new hospital user would have to supply 1 year's worth of hospital data. The Met Office provides 1 year's worth of historical temperature data, which is fed in automatically into an emissions model, which is that YIJN model I showed you about with the Bayesian component. The model is automatically parameterized on the computer. It doesn't take very long, and that then gets fed forward to the emissions forecast stage. Likewise, the length of stay model is built using the hazard rates model. Then in a real-time setting, on a daily basis, the hospitals log in, or at 8 o'clock every day, the Met Office puts out the 7-day temperature forecast. This gets fed into the emissions forecast model, which is run 10,000 iterations, which gets fed in then to the occupancy forecast model for bed occupancy, which is combined with information that the hospital might want to include about the current snapshot of occupancy. So with all that information combined, we then actually produce our summary forecast, like the graphs I showed you. So this runs 10,000 times. This runs 50,000 times. On our computer in the office, it takes 8 minutes. On the Met Office supercomputer, it takes 1.5 seconds. So it shows that computational time is not a problem with their supercomputer. And so very rapidly, the hospitals get forecasts for the next 7 days. And at any point in time, the hospitals might, for example, upload new current data, and they can get revised forecasts for the next 7 days. So they, for example, could have a midday occupancy, a midday prediction, and then they could have a midnight prediction if they wish to do so. So to conclude then, we've developed statistical models for emission of forecasts, including Bayesian methods for handling uncertainty in the weather. These are currently 7-day forecasts, and we produce associated confidence intervals at minimum for 3 age bands and by gender and by specialties. The hospital feedback was that it's very useful for 7 days, and they've been very accurate, but it would be nice if we could extend them to 21 days, and so we've been working on that. And the problem is that the Met Office is very reluctant to put out forecasts for weather for more than 7 days. You can imagine, particularly in the UK, it's hard enough to forecast for the next 7 days, let alone up to 21 days. But we can still build models based on the other components to produce forecasts for 21 days out. We capture length of stay using hazard rates. We simulate for bed occupancy predictions. I should have mentioned the code is built in C and some aspects of R as well, and that's all sits on together on a Met Office computer. And the model validation is important, and I've talked about that. And we've got ongoing pilots. We're actually now about to expand it into to 7 more hospitals who are going to pilot it as well for a longer period of time. And it sits on the Met Office server with a user-friendly web interface for use by the hospitals. That's the MetSim team. That's Sujit and Bernard, who are working at Southampton. Bernard's a postdoc, has now moved on to actually warmer climes and is gone to Australia, where I suspect cold weather in Brisbane doesn't really have such an impact as it does in the UK. Maybe he should be modelling heat stroke rather than cold weather. That's myself and my postdoc John Minty, who have been working on more the length of stay components and the coding for the MetSim tool. Finally, a quick plug about a new journal I'm one of the editors of, which is an exciting new venture, Health Systems, published by Palgrave Macmillan for the UKOR Society. If you want to take more details about that, the first issue is now out and it's freely available online if you want to Google Health Systems and find out more details. That's it. So thank you for listening. If you've got any particular queries or want to contact me, then my web address is given there.